All right, here we go. We are going to solve each of these systems here, and we're going to use a matrix inverse. Okay, so a couple of things real quick before we get rolling here. We want to notice a few things. All of these matrices, whoops, didn't do my little curly bracket. All of these systems, rather, all of them have the same variable part, right? So this is the same for all of these systems, right? So the only thing that changes with these guys are those numbers right there, right? So in general, we can rewrite this as a matrix equation where I'm going to have something that looks like this, where A is a matrix and B is a matrix. So if I knew what the inverse of A was, I can multiply on the left by A inverse on both sides. And then that's going to get rid of this guy. And I'm going to be able to say what my solution is, right? So I'm not quite confident. I mean, in each of these, that's going to be B, right? B is this 2x1 matrix that is going to represent your constants there, the non-variable terms. So what we want to do is we just need to find that inverse, and we can just apply the nice, the inverse property and multiply on the left by our coefficient matrix. So let's go ahead and find the inverse. So let's find A inverse for A equal our variable matrix. So just the variable stuff. So we're going to put 2, 1, 5, 1. And we want to find that inverse. Okay, well, we can do this in a couple of different ways. But the way we're going to do it right now, we're going to take and put this in what the textbook calls a supersized matrix. So we're going to put all of these values over here on the left side. And I'm going to put a line there, and I'm going to put the identity over here. So the 2x2 identity. So what we're going to do here is we're going to go through our the Gauss-Jordan elimination, and we're going to write it like this. And if we can, there's our inverse. If I'm going to take these numbers here, and we're going to do row operations until we have that in reduced row echelon form, right? That's what Gauss-Jordan elimination means. Okay, well, let's do it. I don't know. Every step of the way here, we really want to make our lives as easy as possible here. And I can kind of see into the future where I'm going to have to deal with goofy fractions. And I want to kind of avoid that as much as I can. So I'm gonna just put row 1, and I'm going to replace row 1 and row 2. I'm going to interchange them. So that's all I'm going to do for the first step. So I'm just taking my second row. It's becoming my first row. And then my first row is becoming my second row. Okay, great. So now I can take a multiple of this second row, and I can subtract it from that one. So I'm going to take row 1, and I'm going to take off 2 times row 2, and I'm going to put that in place of row 1. Maybe make that arrow a little longer. Okay, so that's going to give us a 1 in this position, right? And that's good. So I'm going to take row 1. I'm going to subtract off 2 times row 2. So I got row 1 minus 2 times 2 is 4. So 5 minus 4, that's 1. Good. Then I've got row 1 minus 2 times row 2. So I got 1 minus 2 would be negative 1. Okay. So row 1 minus 2 would be negative 2. Row 1 minus 2 times there would be 1. So we didn't change row 2. So we got 2, 1, 1, 0. Okay, good. So now that is wonderful because I've got a 1 in this position, and I can use that to cancel out that 2 there. Okay, so now I'm going to take row 2 and subtract off 2 times row 1, and I'll put that in place of row 2. And that's going to get rid of my get rid of my 2 in this position here, right? Okay, so row 1's not changing. I'm just going to copy that guy down. Probably writing that a little bit wide, right? We'll be okay. So I'm going to do row 2 minus 2 times row 1. So I got row 2 minus 2 times row 1. So 2 minus 2, that's 0, what I wanted. I've got row 2 minus 2 times row 1. So 1 minus 2 times negative 1. So that's 1 minus negative 2. So that's 1 plus 2. So that's 3. All right. And then we do the rest of them. So row 2 minus 2 times row 2. So that's plus 4. 1 plus 4 is 5. Okay. That's wonderful. Now we have, don't know why I'm pointing to that one. So I'm going to do row 2 minus 2 times row 1. So row 2 is 0, minus 2 times that would be negative 2. All right, good. And now what? Well, the next step, of course. So now here I want to get a 1 there. So we're not going to really do much in this step. So we're just going to take 1/3 row 2 and put it in place of row 2. And I'm hoping I can squeeze that in there. Sure we can. 1, negative 1, negative 2, 1. And then we've got 1/3 of that row. So I've got 0 and a 1. And then 5/3. And then negative 2/3. Okay. And now we're in a good position. We got one more step and we're done. All we have to do is just add these together, right? So I'm going to take and I'm going to do row 1 plus row 2. I'm going to put that in place of row 1 and we're going to be done. Alrighty. So row 1, that's the one that's changing. I'm going to add the 2 rows together. That's all we're doing. 1 plus 0, that's 1. 1 plus negative 1, that's 0. 5/3 plus negative 2. So 5/3 plus negative 2. Negative 2, that's 6/3. So if I add those together, I'm going to get negative 1/3. Okay. And now here I'm going to add these 2 together. And we've got negative 2/3 plus 1. So 1 is 3/3. So I'm going to get 1/3 up there. Great. And then we've got the bottom row didn't change. We've got 0, 1, 5/3, and negative 2/3. Okay, so what we did there was, well, this, right? We took our original variable part of the matrix and we set it in the supersized matrix with the identity of the same size. And we use that nice Gauss-Jordan elimination to put this in reduced row echelon form. And now this object here on the right side is our inverse. So right there it is. How great. Now, if you're not just totally and completely confident that this is the inverse, go and check it, right? We need that. We multiply the original matrix, so 2, 1, 5, 1. And if we multiplied that by this guy, that ought to give you the identity matrix. And I don't know, maybe you hit pause on the video and verify for yourself that's true. I already did this ahead of time, so I know that that's true and I don't really need to go and check it. So I'm not going to do that. So let's, yeah, hopefully you checked that and you verified that was true. And let's remind ourselves what it was that we were doing. Oh, I've got that written right there. So here's what we were originally doing. It's kind of a little scribblier, isn't it? Okay, so we want to take these and solve them. What we said, let's just gather together what we've done so far. So we said that the matrix A was 2, 1, 5, 1. And we found that the inverse was this other matrix here, negative 1/3. I'm just copying it down from what I had before. Nope, that's a 3. 1/3, and then negative 2/3. Okay, what we found was that was our inverse, right? Okay, so real fast, structure-wise, what we already wrote was that all of these looked like A times X equal B, where A is this matrix. X is our variable. Well, right, those were our variables. And we can take and do matrix multiplication there, and you know, we're going to pair up the x's with all of these things. We're going to pair up the y's with all of these things. So then we had then our other matrix, right? So let's take just this guy here, right? We're going to hopefully see the idea almost immediately. Well, this is my matrix A. So if I take and I multiply my inverse of A on this left side, then this is going to become the identity. That's just essentially going to go away, right? So this guy is sort of canceled out. And then on the right side, I'm going to have to multiply by my matrix inverse there. So this is going to give you an equation, x, y equal, well, this is going to be what we want. And we can find it, right? We're just going to take our inverse matrix. So I got -1/3, 1/3, 5/3. No, that was positive, wasn't it? And then -2/3. Okay. And I'm going to multiply that by 1, 1. All right. So I guess, you know, going down the line here, we're still doing this process here, right? So we can do the multiplication, right? So I've got my xy is just going to be the product here. So I'm going to take my rows. I got row 1, row 2. I'm going to take that by column 1, right? Because this is a 2 by 2 matrix. This is a 2 by 1 matrix. So my product is going to be, well, a 2 by 1 matrix, which is exactly what I want. Okay, so we can do that. We've got this guy here times this guy here. So in the top, I've got -1/3 times 1 plus +1/3 times 1. Okay, and then in the bottom position, I'm going to have this guy. So I've got what? 5/3 times 1 plus -2/3 times 1, and that's going to be my matrix there. And we can add these things together. So I've got -1/3 times 1, that's a -1/3, plus 1/3 times 1, so that's -1/3 plus 1/3, that's 0. And then I've got 5/3 plus -2/3. Okay, so I got 5 minus 2 is 3 over 3, that'd be 1. So we found the solution. Our ordered pair xy is 0, 1. And we can go ahead and go plug that back in to the original equation. So we got 0, 1, and maybe I'll write that up here. 0, 1 is the solution. And we can go ahead and plug that in and verify that it makes it true, right? I put a 0 here and a 1 here, that I do get 1. I put a 0 here, a 1 here, I do get 1, right? So that checked out. Okay, so what are we going to do here? Let's do a lot less work for this one. So we don't need to write all of this nonsense here because we're just going to do the same thing, right? All we really need to do for this one is we just need to take and say, hey, my xy, this is going to be my inverse matrix times these numbers. So again, the inverse matrix, we got -1/3, 1/3, 5/3, looks like an S, and then -2/3, okay. And we're going to multiply that by our coefficients here, so 3 and a 6. Okay, so we're just going to do the same steps, right? We got this guy times this guy, so I've got -1/3 times 3 plus 1/3 times 6, and then we've got the second row times that column, so I've got 5/3 times 3 plus -2/3 times 6. And that is my matrix. We can do these first Thursday of the month, right? That's I don't know if you heard that. It's a tornado siren going off. Anyway, we can add these together, right? So 3 times -1/3, that's -1. plus, what is this, 2? So negative 1 plus 2, that's 1. All right. And then we've got 5/3 times 3, that's 5. And we've got negative 2/3 times 6. So 6 divided by 3 is 2, times 2 is negative 4. So I got 5 minus 4, that's 1. So that would say that our xy is the ordered pair 1, 1. All right, I was off the screen there. So let's take now and go plug this back up into here and see if it made it true. I can put a 1 here and a 1 here. 1 here and a 1 here. I got 2 plus 1 is 3. That's true. 1 here, so that's 5 plus 1, that's 6. That worked out. Good. And now we can go ahead and find our third solution. So I can take my coefficients over there and just multiply them by that inverse matrix again. So yeah, I mean, once we find that inverse, it's kind of smooth sailing from there, right? So now I'm taking my third one, and I can do this. So this would be row times column. So I've got negative 1/3 times negative 3 plus 1/3 times 9. And then I've got 5/3 times negative 3 plus negative 2/3 times 9. And we can say what that is pretty quickly, right? Negative 1/3 times negative 3, that's positive 1. Then this guy is, what is this? 3? 9 divided by 3, that's 3. And then if I do, that's 1, so that'd be a 4. Okay. And then I can do these as well, right? This is going to cancel and become a negative 5. So negative 5 plus, what is this? 9 divided by 3, that's 3 times 2 would be 6, so negative 6. So we've got negative 5 minus 6. Negative 5 minus 6 would be negative 11. I screwed something up there. Let's go and you know, maybe we didn't. So let's take it. So we're saying xy here would be 4, negative 11. And we're going to probably be able to tell really quickly whether or not we screwed this up here. Now 4, negative 11. Let's find out. Does it work? So I got 4 times 2. Whoops, I'm off the paper there. So 4 times 2 is 8 minus 11. Well, that gave us negative 3. That's good. 4 times 5 is 20. Minus 11 gave us 9. So it worked. I was thinking that it didn't work because that's not the problem that I had initially written down. I screwed up and I wrote a 9. Anyway, we found that it worked and we just plugged it in. So I don't know. We can probably argue back and forth as to whether or not using matrix inverses is easier for a single system, but it is absolutely easier to use matrix inverses if we're going to try to solve multiple systems that have the same variable parts.